60 up there. Two, 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 two. So look at that for a moment. Hopefully it looks a little familiar to some people. Now, this one is, this poor little book. Poor little book. People didn't pay much for it. It's doing its best. Which information is extraneous that we don't need? Can you tell? Look at the first sentence. What data are they focusing on? What is this weird little dude? I don't know. Yes, poverty rates and cell phone usage. So what did they give us that we don't really need? Year. Okay, good. That's just extra information they gave just to mess you up. No, just to, mess you up. So when I go to put this into my calculator, L1 poverty rate, L2 cell phone usage. Yeah. Does that make sense? So they... this is kind of like real life. Real life, you're going to have all this kind of data, and you've got to kind of pick the ones that are most important to you. And that first sentence tells you, focus on these two things, right? This isn't a question about does year affect either of these things. It's do they affect each other. Is that all right? Kind of the next level of stuff beyond what we end up in this class is how do I look at all the variables at once. So what I mean by that, when we do correlation analysis, we only investigate does one variable have a relationship with another variable. That's all we look at, correct? And in fact, I asked you guys, are there other variables that would affect your grade beyond how much beer you drank the night before? And you all appropriately said, yeah, right? You didn't say it like that necessarily. You guys kind of with me? So there's all these other variables, and with linear correlation, we can only look at two of them at a time. There are statistical analyses that can look at multiple variables at once. That would be one of the first things you would do in a Stats 2 class, right? Anyway, so everything I just said has nothing to do with you at the moment, so sorry. So yeah, is that better for that one? Yeah. Okay. Maybe I don't want to do that one because it's your homework. Let's do a practice problem, just to get back in the flow. I think does anyone here right now didn't get the worksheet stuff from Monday? I think everybody got it. Okay. Good. If you weren't here, you desperately want to watch that video. I don't have my channel monetized, so it's not for me to make more money. If I did, I wouldn't blame you if you never looked at any of my videos. All right. Let's see. Do I want to do one out of here? These are gross. Yeah, this looks good. So let's see. Oh shit! What did I just do? There we go. Let's try this data here. Does anyone need to borrow a calculator? Let's do that. Calculum millimeter. You're welcome. Make sure it's got battery. Okay. Okay. All right. Let me see if I can do this. Can I be this nifty? I don't know. I think so. Sure. Okay, let's see. Okay, so let's see. Let's put this data in. Give me a second. Let me close the grades so I don't accidentally flash everybody's grades up here. Okay. Which one was I looking at? This one. Okay, nice. So, if you weren't here yesterday, or if you just forgot what the hell we did yesterday, let's do this. So I'm going to put into L1, I'm going to clear it, I'm going to put the number of driver deaths. That's a good choice, Jeff. Good job. Wait a minute. Is this what I want? Yeah. Where'd it go? Oh, I see. This is a little bit weird. Why do they have to be weird? Nah, let's do a different one. Sorry. Yeah, we'll do this one. The one I was looking at here, they said to pick the midpoint of this since there's, multiple values. I don't want to mess with that. Let's just look at this guy. The next one down. All right, so sorry guys. So let's start over. Put the year of birth in the list 1. Oh shit. No jump. I think that's all of them. Yeah. And then list 2. We're going to do clear. And then we're going to put life expectancy. Look at that. These poor fools back in the day. Where am I at? I'm coming up here. Oh, shit, I'm going to die soon. All right. Let's see. 5. All right. Recent life expectancy went down, not surprisingly, because we had a worldwide pandemic. So, life expectancy actually went down for the first time in a long time. All right, I'll give everybody a minute to catch up to me. Okay. Does anyone remember where to go to get the information we need? What 2 things do you need to calculate? What 2 things do you need to calculate? The line of best fit. What does the pirate say? There you go. So we got to calculate the line of best fit and R. Okay. What does R tell us? What about correlation? Strength of the correlation. I love it. Right? What would perfect positive correlation be? R would be 1. What would perfect negative be? That's crazy. What would no linear correlation? R would be 0. I love it. Okay. So again, just to remind you guys, it goes in line with something I kept saying the whole semester. Every time I give you new data, we have to find a way to get the average and the standard deviation. In this case, the line of best fit is like an average, and the R value is sort of like a standard deviation. What buttons do I push to make this thing tell me all this stuff? Stat is a good start. I like it. Stat, calc. 4. Make sure the freaky list is empty. If you have a calculator, it just says linreg. Just hit enter because it defaults to list 1, list 2. So you can just hit enter right away. Me, I got some other shit to do. So I get down to calculate. Bam. Now what am I missing? R. So, anybody else also only get A and B? Anybody else not get anything else besides A and B? Anybody have exactly showing what I'm showing? Okay. Good. So do what I do. On the calculator. Don't get up and walk around. So hit second 0. That takes you to catalog. Hit the button right here that has the letter D above it. Chaboo! So I go to the D section of the list. And then go down to diagnostic on. You only have to do this once, thankfully. So if you've already done this, you should be good to go. Unless you're borrowing a calculator. Diagnostic on, enter. So now if we go back, stat, calc, number 4. Now I get my R squared and my R showing up. So can anybody tell me anything about what does any of this stuff mean? Is this a strong correlation? Yeah. It's not the biggest sample, but holy shit. What tells me it's a strong correlation? Yeah, 0.96 is really close to 1, right? Also, it tells me that it's, from your perspective, what would it be? Yeah. Positive. Right, so it's a strong, positive correlation. And what's the line of best fit? What is the line of best fit? What is it, guys? Can somebody write it down? What's the line of best fit? 0.23, roughly, right? 0.23x minus 377.2, right? Somebody write that down and tell it to me again. I think it was 0.23x, right? Minus 377.2? All right. It's like I'm good with numbers or something. Now, if I just hit graph, I'm going to get, I could get all kinds of weird shit. How do I make the calculator that costs enough money for it to do this for me? How do I make it find the data I just put in? Zoom? Stat. So for me, it's number 9. Should be number 9 for both you guys. And of course, I forgot. This is for a little calculator. Real quick, let me do this too. If you just did what I did and you still get this, I haven't turned this guy's stat plot on yet. So let me hit. Anybody else get something not showing any data points when you did that? Zoom 9. How many guys got data points showing up when you did that? 4 of you. Okay, that's bad. How many of you guys don't want to raise your hand when I'm asking questions? I like it. Paradox. Okay, so let me try this again. If I don't have data showing up, I'm going to hit second y equals, because right above y equals it says stat plot. That sounds very encouraging because I'm trying to plot statistics. So go to stat plot. I'm going to go to plot 1 and I'm going to turn that on. Bam. I'm going to make sure it's set to a scatter plot so I can just make points. I'm going to make sure my x list is L1, y list is L2. For me, I'm a square. And I'm going to leave it at blue. Why not? So now if I hit zoom 9, now it should find that. Now something interesting. Look at this. What did I do wrong here? What tells me I did something wrong?
It doesn't look right.
Why doesn't it look right?
Because it doesn't look like the line of best fit.
Why? Be more specific. The line should probably be a little
Closer to the points.
closer to the points. So it should be down a little bit, right? So let's see. What did I do wrong? Did I put this in here wrong? Let's see. I got to recalculate. 0.23 and negative 377.2. That's right. Let's see. 0.23. Negative 377.2. All right. Well, that's weird. Oh, we got to be more specific here because we got tiny. Okay. Let's see if this is it. Let's be more specific. All right. Let's go out a few more decimal places here. Normally it's not that big of a deal, but since our slope is so tiny, let's go on a few more. So let's do 0.22748. 0.22748 x minus 377.243. Let's see if this takes care of it. Okay, there we go. Woo! So let's see if I can explain this. The slope is so tiny that any rounding by too much is going to change it by quite a lot. So it wasn't that it needed to be more down, it actually was that it needed to be less steep. I don't know if your guys are with me. So one thing you could do to kind of counteract that, I think I showed you this last time. When you calculate this, if you have this show up, I don't know if you guys remember this. Right here, you can tell the calculator, hey, can you put that equation in for me? So if we hit store regression equation, if you hit distribution right here, if you hit vars, y vars, so this is y variables, function y1. So it's going to store the equation in y1. So when I do this now, if I go to y equals, it's got all the decimals in the, not all of them, but a lot of decimals in there. So now when I graph it, it's going to be spot on. I like it. So on a quiz or a test, if you do something and you know it's not where it's supposed to be, when you come up to show me, I can actually help you figure out what went wrong, right? Okay. That looks a lot better. Do you see a point that's really far away from the line? Like this dude here, right? I don't want to get too much into it. You want either equal points above and below, or do you see what kind of balances this guy out? See how he's so far away on that side? Aren't there 3 points a little bit away on the other side? So they all kind of balance each other out. I don't know if that makes any sense. But visually this makes sense that it should be there. Okay. Do they ask us any more questions? Oh, they ask us a lot of questions. Holy shit. Okay. Yeah, the correlation coefficient, that's another name for what? Correlation coefficient is another name for R. Okay, I like it. Estimated life expectancy for somebody born in 1950. So the actual life expectancy is 70. Does anyone remember how to use the calculator to figure out for 1950? What would the output be? Either you could throw it into the equation we got. You can always do that. How do I make the calculator do it for me? Do you guys remember? I want to calculate something graphically, so I'm going to go to second trace to calculate. I want to calculate the value of something. I want to calculate the value when the input is 1950. Is that equal to the actual expectancy? Remember, the actual expectancy in 1950 was 70.2, right? Why is that not equal to 70.2? Why is it okay that it isn't? I love you guys so much. Was R 1? No, R was not 1. So while the estimation is going to be good, it's not going to be perfect. Does that make sense? If R had been 1, we would have gotten exactly that, because every data point would actually lie on the line. This, some go away from it. Some go a little further than the other ones. Let's try another one real quick. If I do second calc value, let's do 1982. Yeah, that's closer, right? 73.6 versus 74.5. Do you guys see that? Okay. I like it. Is that okay? That wasn't really a lecture, but it was it basically covered everything we did yesterday. So this is the one section that I'm completely fine with everything happening in the calculator, because you have to interpret what you get out of it. All right. And again, one thing I'm going to give you that the book doesn't give you is the R value that you need to show evidence of correlation. Remember that? That's on those handouts we did. I don't necessarily want to do this, but this sheet here, remember this sheet? This was a lot of fun. The one you had to actually do the y minus y1 business. It's out of your memory? Okay. The other side had an example of a problem that I might give you. Yeah. I think I'll probably... well, let's see. Does anyone want to do this one right now? Or I could make an answer key for it and give it to you. What do you think? This is a democracy for the moment. Huh? Let's do it. Let's do it. All right. So let me show you. It's on the other side of... So on the other side of this sheet. See it? See this sheet? Okay. This sheet? Everybody have this sheet? Okay, I'll take that as yes. If you flip that sheet over, let's do it. So everybody should have a calculator, right? Including me. Hey. Let's take a minute. Big part of statistics. Very exciting. Data entry. Oops, Jeff. Oh, shit. Okay. Uh-oh, that one definitely didn't go on. Oh, that one looks bad. Let's see. Yay. Okay. The worst thing in the world is get to the bottom of list 2 and it doesn't match up. And you're like, oh God, which thing did I miss? Now, on one level, do you guys understand it makes sense there's going to be a correlation here, correct? Yes? the percentage of bachelor's degrees in a state versus the median income, there should be a correlation, yes? Now what's interesting is what causes what. So you could think immediately like, well, if you have a bachelor's, you're going to get a better job, but doesn't it cost money to get degrees? If you had better jobs in a state, couldn't more people then go to college because they have more money? You with me? So it could be a little bit of both. One causes the other and vice versa. Are you guys at all with me? So again, even when we have a feeling that, well, it's obvious that you have more bachelors, it's going to be a higher median income, but it could be a little bit the other way too. This has nothing to do with causation. Doesn't mean there is, doesn't mean there isn't. I have no idea. Okay. So what do I push again? What buttons do I press? Stat. Help me. I have forgotten. Calc. You can do 8 if you want to. I always do 4, but you'll get the same stupid numbers. They'll just be switched, right? You can do 8 if you want to. It's okay. And then, again, does anyone, when you do what I just did, does it just say linreg on the screen? Does it just say linreg? Does anyone not get this whole list of crap? I kind of am a little jealous. It defaults to list 1, list 2. You just hit enter. Me? Enter, calculate. Okay. Let's see if y'all get the same numbers. I can't remember what they're supposed to be, but hopefully this is right. Anybody else get those numbers? Yes? All right. We're both wrong. I love it. We can be wrong together. Anybody else get those numbers? Yes? Okay, good. I feel a little better. Looks like we might be okay. Okay. Anybody not get those numbers and actually wants to let me know so I can help you?
You did it, but you only had the first two.
Oh, gotcha. Yeah, so I don't know if you were, I showed this earlier, but you only have to do what I'm about to do once. So I'm really there if you're, so you want to, all this does, once you do this, you're set. Blah, blah, blah. So, first impressions. It's a decently big sample, right? It's definitely bigger than the last one we did. So couple that with the fact that what? It tells me it's strong correlation. R is pretty close to 1, right? 0.92. And it's a decent sized sample. And again, we sort of expected this, right? On one level, it's like, well, yeah, if you have a higher percentage of bachelor's degrees, you're going to have more people making more money. But again, like I said, you don't know which way that kind of goes. My poor little calculator's like, I'm done. Okay, so I would say it's not a bad idea, especially with that last problem. Most of the time you're going to get slopes and such like this, where if you round a little bit, you're fine. If the number's pretty small, rounding by a little bit is relatively a lot. So let's see. Let's do 1570.74x plus 12,231.47. Real quick, what's the y-intercept? What's the y-intercept? That is so true. What is it? What's the number?
12,201.46.
What happened? Oh. That's a neat, you were the right answer too. That's crazy. All right, just don't do shit, all right? Just hang out. 12,231. What does that mean? Don't fixate on the B. Don't stare at me, he's self-conscious. What is that, what's a y-intercept mean? What's the y-intercept mean in general? That's when what? When x is 0. What's the input for this problem? What's the input? What was the first column? That's my x's, right? The first column was what? Is everybody staring at me? I understand. First column was? Percentage of bachelor's, the percentage that have bachelor's degrees, right? So if the percentage that have bachelor's degrees is 0, I would expect a median income of 12,000. Does that make sense? Why not? I would expect the median income to be lower, right? If I had 0 people that had a bachelor's degree in a state, I would expect the income to be lower for that state. Does that make sense? Because in general, the higher paying jobs require higher degrees. Now, I will admit this, you've got a lot of trades that you can learn in the trade. It's not a bachelor's degree. In some respects, it's better. You have a good skill you can use, and you're going to make a decent amount of money. Electrician, carpenter, all that kind of stuff, you can make a decent amount of money. You could also make nothing if the economy or the requirements are just going down. What's the more important thing here, though? What's the lowest percentage, roughly? Looks to be about 24, not to pick on Oklahoma, but, right? Does anyone remember when I'm looking to make predictions, what do I have to be careful about? Could I use 0 as an input to make a prediction? I love you guys. You're all staring at me like. We found a correlation that works for percentage of bachelor's degrees from 24.8 up to, looks to be 42.1, right? Are you guys with me? I cannot use numbers outside of that range to make predictions because our line only works for data from that to that. Okay. Hopefully, yeah, that's not a sign of something more. Okay. Are you guys at all with me? Can somebody give me an example of an input I could use? What's a percentage of bachelor's degrees that I could use as an input to make a prediction? What if there was a state that had blank percentage? 30%. Say again? 30%. Yes, 30%. Why? It's within the range of the data that I used. I couldn't use 15% because it's not the range of the data that I used. Good. Okay, I like it. So we found the line of best fit. The R was, what was it, 0.92 something, right? 0.24? Okay. So of course, when I say interpret R, that just means is it strong, positive, weak, negative, whatever. This would be strong, positive. I like it. What does this R tell us about the line of best fit? Now let's see what you guys say. What does that R tell me about the line of best fit? There's a couple things I would accept. Would I trust the line to make predictions within the data? Yes, so you can either say we would trust the line. I really don't want to write today, it looks like, to make predictions. You could also say what's true about all the data points in relation to the line. They should be close. I say like tight to the line, close to the line. Either one of those are acceptable. This is exactly the kind of question I would ask you. So when I ask you, what does this tell us about the line of best fit? You could either say, I would trust it or not trust it if there's no correlation. Or you could say all the data points are going to be really close to or tight to the line, right? Okay. Okay. So is this an acceptable number for a prediction? Yes. Is he still right there? Yeah. Okay. Poor little dude. He really likes that light. Okay. So take a minute. How do you make a prediction? What do you do? I get out my tarot cards? No. Maybe not. Get some tea leaves going. By the way, real quick, this is something you're not used to. We constructed this equation. We constructed it to handle percentages. So if you are making this into a decimal, part of me loves that shit because in general you're supposed to make it into a decimal. We created this equation to handle percentage inputs. Do not make this 0.376. That would be a state with 0.376% having bachelor's, which is kind of low. So I'm going to put in there 37.6, and then I got, what was it, plus 12,231.47. Don't forget the 47 cents. So that's what I get. Real quick, why do I say compared to Virginia? See how I say compared to Virginia? Because it's the same percentage. Did we get pretty close? Yeah. Why is it so close? Why did we expect it to be pretty close? Because ours close to 1 is strong. Why is it not exactly the same? R is not perfect. Our correlation is not perfect. You guys all with me? Okay. 11. Some of you guys are like staring into my soul. Okay. Somewhere in there, there's sense. So what do we get? We got 71,291. When I say compare to Virginia, actually write something close to, where'd it go? 71,585. 535. You could do it, Jeff. All right, now the critical one. Read part D and think about it. So who thinks they have the answer to part D? Not part B, part D. Who has the answer to part D? Anybody? Who has an answer and you're like, you're not grading me right now, so it's okay if I get it wrong? Anybody? Now's the time to get it wrong. Tell me, just what's your immediate reaction? What would you say? Okay, I get some people, yes. Okay, you're all wrong, but it's okay. Sorry. So again, this kind of analysis, now, including all of our experience already, we kind of know this makes sense. Yeah, if you suddenly get more bachelor's degrees, they're able to get better jobs and so forth. From just this study that we did, it tells me nothing about causation. So do your results mean that if you do this, it will increase? No, I have no idea. Right? Maybe there's a state that if you give them more bachelor's, there's not very high-level jobs in the first place. So they still end up getting the exact same job they would have gotten. Does that make sense? So I can't say, I really need you guys. So this says nothing about causation. I just know there's a relationship. I don't know if one causes the other one. Right? Okay, you all look very excited about this. So basically, if I ever ask this kind of question in a correlation problem, your answer is no. Not necessarily. Does it mean that it won't happen? No. I don't know. We don't know. This is not set up to be an experiment. We didn't go in and change anything. We're just observing. It's not a causation experiment. I can't tell. Okay. Why or why not? Because this is just a correlation study. It's not a causation study. Okay, maybe. A causation study would be, the standard example is a drug. You actually give a drug to people, and you don't give the drug to the other people, and you look at these people and you watch them and see what's going to happen to them. I did something. I didn't just sit back and observe. You guys semi with me? Okay. Okay. Any questions on that? I normally, and I understand that students are cooler with this than with some of the stuff we've been doing recently, because this is a little more concrete, right? You can feel hypothesis tests are sort of like, bleh. Okay. All right. So what we're doing today is you're going to get your last chart. So we got z-score charts, we got t-score charts, and now we're going to get our last one today, right? Little tear, aw. What we're going to get into, somebody tell me, what kind of problems have we done that use a normal distribution? I'm asking you this because I know you all love when I ask this kind of question. Can somebody give me an example problem where we used a normal distribution? So let me get one started. They give me a mean and a standard deviation, and they ask me what kind of question. So if I gave you a mean and a standard deviation, what question would I ask you? And I tell you it's normal. What question would I ask you that you would have to use a normal distribution to answer? Give me an example. The probability that. What kind of question would I ask you? I know, you still. If it would just go towards the door, we'd be great. All right. All right. Anybody? I'll do the next step. All right. Probably x is greater than, sure, greater than 5. Okay, 11. There it is. Beautiful. That's an example question I could ask you, right? Now some of you guys are like, oh, that's what you wanted. I know what the hell you want. You guys kind of with me? I'm given a mean and a standard deviation, right? What does the standard deviation tell me about the normal distribution? What does a standard deviation tell me about a normal distribution? So if the standard deviation was 3 versus the standard deviation being 57, what would be the big difference? Sure, but in terms of shape, what would be different about the shape of the distribution? What does the standard deviation tell you? What does it tell you? Sure, the spread of the data, right? So can anyone just tell me, how would those distributions differ? One of them would be a lot. I hear words. What are they? I can't tell what they are. Smaller is not quite good. Smaller could mean just like same shape, just skinnier. There it is. Which one would be skinnier, of course? This dude. So this dude only gets 3 away, whereas this guy gets yeah, right? Could I draw the picture if I didn't know what the standard deviation was? No. Okay. So that's first thing I want you to realize. Is everybody with me? I knew you guys knew this. You just weren't sure exactly what I was asking, which is fine. It's just my job. That's all. I can't do it. How do I make this picture? If I have a normal, if I know there's a normal distribution, how would I create the picture? So we did this when we went to Alternate Universe, Florida, right? I don't know if you guys want me to bring that up, but does everybody remember doing that? We had a little field trip, sort of, right? In our imagination. I could go around and say, so I could have a blank slate. I can go around and say, how old are you? I'm this old. How old are you? I'm this old. How old are you? I'm this old. Right? And eventually, it would build up to be this. Are you guys all with me? If I know it's normal already, if I go around and capture all the data and I plot it, it would make that shape. You guys all with me? Okay, and what is it that I'm plotting? I'm plotting ages. I could also be plotting means, right? I could be plotting sample means, which is the whole central limit theorem. Okay, so what we're about to get into, one of the most fundamental uses for it is, what if it's the standard deviations that I plot? If I go take samples, I can figure out a sample mean, correct? And if my sample sizes are more than 30 and I plot them, I know it's going to come out to be a normal distribution. You guys all with me, right? It's old shit. We know the shit. If I take a sample, can't I also calculate the sample standard deviation? Yes? What if I plot those things? What shape would it take? Would it necessarily be normal? Remind me, what tells me the shape of this again? The standard deviation. So what if I have a bunch of standard deviations? What shape is that going to be? It doesn't have to be normal. In fact, the standard deviation would tell me what the shape is. What if I have a bunch of them and I'm plotting them? What the hell shape is that going to take on? So here's what it does. Okay. For degrees of freedom, oh shit and a half. Poor little dude. Okay. Are you doing all right? Sort of? For degrees of freedom greater than 1. This is going to look like this. You ready? All right. Can somebody tell me what is the smallest the standard deviation can be? Can a standard deviation be negative? Anybody know what's the smallest that a standard deviation can be? I think you guys are saying it. I'm not sure. Got to learn how to read lips. Some of you guys are like 0, right? If there's no spread, you can't have negative spread. That makes no sense. Can somebody tell me a set of data that would have a standard deviation of 0? Anybody? Give me a list of numbers that would have a standard deviation of 0. You could do it. Say it. 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. 2, 2, 2. Yeah. Right? If they're all the same damn number, how far away do the data points get away from their average? 0. The minute any of them aren't 2 anymore, standard deviation gets bigger than 0, correct? So the smallest it could be is 0. It's sort of like you can't have a negative distance because then you would be like inside of me. Little quad of Quaid. No, okay. So our picture for this will always have a wall at 0. It can't go below 0. So here's what it's going to look like. Let me draw it and see what you guys remember what this is. And I told you this was coming. Is that normal? No. Ah, there it is. Skewed. Right. So remember, how do you tell which way skewed is? Which way did you grab onto the normal curve and pull it? Somebody grabbed on this side and pulled it, right? And again, silly Jeff calls this the Jabba the Hutt distribution, but that's okay. You don't have to do that. So this is skewed right. Okay. So if I took, and let me be a lot more specific. If I took a bunch of samples and I found sample means, right? And I knew the standard deviation of the sample means. Are you with me? I could then calculate a z-score. And that would show up in the distribution. Are y'all with me? Okay, this is all shit we've talked about before. There is an analogous formula for standard deviations. The symbol we use for this distribution is chi, right? Nothing to do with Jack. Chi squared. So that is one symbol. So this is chi squared. Okay. So it's just like z. It's exactly like z. It's just another freaking symbol. I'll talk to you why it's got a square on it in a minute. Stay with me now. Okay. Is everybody cool? This shit right here. This shit right now, you all should be like, yeah, give me that shit. I can do that. So I can calculate a z-score for any sample mean that I calculate. Now, I go out, take all those same samples, and I look at S instead of X bar, right? And I calculate this. What part of that looks, well, all of that should look familiar. That is the sample standard deviation, right? That is the population standard deviation. This, degrees of freedom, yes, okay, I like it, right? Kind of nifty. This formula is analogous to that formula. This formula will tell me where I am in this distribution. So if I get 0.1, then I'm down there. You know, it kind of depends on, I have to know a little bit more. Just like here, if I got a, you know, here's nice because if I got a z-score of 1, I know it's over there. This one's a little bit freakier than that. I'll show you in a minute. I'm going to give you the table. Let's do it right now, actually. I'll give you this table. Okay. So exciting. Our last table. It's like I'm not good with numbers, but I'm glad that worked out. All right, guys. What on there? Anything on there look familiar at all? Something should immediately look familiar. And degrees of freedom. All right. Now, basically everything else is freaky as shit. One immediate thing that is very evil, and it was purely done because we wanted to be evil. The z-score chart. Real quick, look at me. Z-score chart tells you the area where? When you look up a z-score, it tells the area to the left. What does this chart tell us? Yes. That is evil. Too bad. I was not involved in the meeting. But, oh well. Okay. Do me a favor. Anybody have their calculator ready? This is going to sound so weird. What is the square root of 2.706? Anybody? Say again, sorry. Does that look familiar? What is the square root of, what's this one? 3.841. .96, is that familiar? A locket, and blah, 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 blah. So, fundamentally, what a chi-squared distribution is, what it's set up to do, is it's the sum of squares of z-scores. So when I look at a degree of freedom of 1, when my degree of freedom is 1, it's equal to the square of the related z-scores. Now, real quick, is everybody, all right. That's just how we sort of built this. So that level, you just like accept it or not. That's just the way it is. How does this relate then? Can anyone remember 1.645? Does anyone remember what the confidence interval was for that or anything? Does that stick in anybody's head? 0.05 for a one tail, so it'd be 90% confidence, it would be alpha 0.10, correct? So how much in each tail then? If it's 90% confidence, how much is in each tail? Oops, sorry. 5%, yes? All right, stay with me. So what this is if I took it right down the middle and I folded that shit on top of itself. So this plus this is 10%. But then I do this times this to get 2.706. Now, how much of what I just said do you actually have to understand fully to be able to do the problems we're going to do? Zero of it. But I do want to show you kind of like where this comes from. So the power of this. So on one level, if we had a situation where we just had degrees of freedom of 1, we would just use a freaking normal curve. We would just use a z-score. This would be extra shit. The power of this is I can have more than one thing I'm looking at. I can have multiple levels of shit that I look at. So we're going to see this in a minute. Okay, maybe. So like this next one would be z-score of degrees of freedom of 2 would be this next row. We're not going to drill down that deep. I just kind of want to let you know, because I like the visual of it. Think about a normal curve. Fold it on itself. Bam! Multiply the z-scores together, add the areas, and you get this first row. The other rows are a little more complicated. Okay. So what this thing does for me is it tells me how things like standard deviations, how they're distributed. And really, why is that? Because we didn't really have the most time in the world this semester to say this, but do you guys remember where we first did variance? What was variance? What was the population variance? So remember that we had population standard deviation, we had population variance. What was the variance?
It was the standard deviation
Squared, good. So what this guy is good for, and the reason that that's right, celebrate. The reason why the symbol has a square in it, this guy is good for distributions of squared parameters. That's what this guy's good for, right? It can handle, the first row captures the standard normal distribution. Then I got all these other rows that I can play with. I got a lot more I can do. So let's get into that. Real quick, how do I use this? So here's what the picture looks like. For degrees of freedom greater than 1, I'll say that again. It looks like this. Wee-haw. So if I had alpha equal to 0.01, and it was this tail, and I had degrees of freedom of 6, can somebody tell me what the chi-square score would be? So I have a right tail, alpha is 0.01, degrees of freedom is 6. What would the chi-square score be? Chi-square score. I think I heard it. So again, what's it tell us? Area to the right. What's the area to the right of this chi-square? 0.01. Area to the right, 0.01. Degrees of freedom is 6, so then I get 16.8. That's right. You got it. 16 point. Somebody comes in strong in the chorus. I like it. Okay. That's how you read this. The test we're going to focus on is going to always be a right tail test. You could have like left and right tail test. One thing I want you to immediately realize, what is this again? What is this? What's the smallest the standard deviation could be? 0. What's the smallest something squared could be? A real number squared? 0. Is everybody with me? You guys with me? If you take a real number and you square it, the smallest that could be is 0. Is everybody cool with that? Okay. will this be symmetric? There's two reasons it won't. One thing is I can't do like negative 1.96, 1.96, like in a z-score, because again, this doesn't go negative. Also, is this picture symmetric? Shit, no, because somebody pulled it out, right? So there's no symmetry here. So I'm not going to expect to get the nice down and up kind of thing going on with this. Okay. All right. That's the fundamentals of this. So let's take a look. What kind of problems are we actually going to use this for? So the most fundamental definition for chi-square is this one. And that's the one I showed you already. That's one I think we're probably actually not going to use. We'll see. It depends on how much time I've got to do this. That's section 11.6. So we'll see. I'll let you know. The one we're going to use first is related to this kind of problem. Let's say that, what's a good example? Okay. Yeah, sure, I'll do that. We want to see, we have an idea about how grades are distributed in a certain class. Let me say this again. We have an idea about how grades for a population of students in a certain class are distributed. Is everybody with me? So, for example, let's say that we believe there will be 10% of the students will make an A, 20% will make a B. What do you got, Jeff? 35% will make a C. What is that? Okay. 25% will make a D. What does that leave me? 10% will make an F. Okay. For some reason, we feel this is the way it's going to be. You guys all with me? No. Are you with me? Are you with me? Now, listen. Why is it exactly this? I don't know. It's just somebody feels this way. So I can make a claim about anything. And one thing that statistics does is, here's several tools to investigate the claim you just made. What could that claim be based on? Normally, you want that claim to be based on observations you've made, theoretical things, so forth. This is just somebody who thinks, I think it's going to be this, because it's what I've seen. Okay, so it's based on their observations. So then they take a sample of students' grades. Let's say that we sample 200 students. So let me ask you right now, can you take a minute and tell me, let's do this. Make a little table like this. I'll tell you what this is in a minute. This stands for expected. How many A's do we expect to see? If this is our expectation, how many A's would we expect to see? Well, what percentage of A's do we expect to see? And how many students did we take? 200. So I'd expect to see 20. Is everybody with me? Does everybody see where 20 came from? I expect 10%. I took 200. I expect to see 20 A's. All right, keep going. How many B's do I expect to see? 40. Is that cool? How many C's do I expect? 70. How many D's do I expect? Let's say it again. 50. And how many F's do I expect to see? 20. What's a quick check to make sure everything looks good so far? Add them up. See if they make 200, right? 200. All right, sweet. All right, let me stop for a minute. Do you see how we are looking at multiple categories of things? We're able to look at multiple categories at once. What do I mean? What's the categories in this problem? What are the categories? The grades. So there's 5 categories. A, B, C, D, F. We're able to look at more than just one thing at once. We're able to look at multiple categories. Now, this stands for observed. I really want this to make sense. If I have a prediction I'm making, what's the best way to test it? Go make observations. See how close our prediction came from what we observed, and I can see if my model kind of stands that actually passes the test. So let's say we take these 200 students and we look at the grades, and we get 21 made an A, 36 made a B, 69 made a C, and I got to keep track of where I am. Scheisse. 55 made a D. What's that, Jeff? I don't know. 126. 126. 181. Is that right? 19. Is that right? Shit. Somebody double check me. Does that look right? 90. 126. 181. Yes. Okay. I like that. Somebody was like this. Oh. What am I trying to do right now? I'm just trying to make sure that they actually add up to be 200, so I didn't kill people or I didn't create people magically. And I'm pretty sure that adds up to be 200. What do you think the immediate next thing I'm going to do to try to investigate whether my prediction was close to what I observed? What can I immediately do with that data? Was I close on the A's? How close? How close was I on the A's? I was only one off. Okay, how'd you get one? What'd you do? Holy shit. Okay, so the next immediate smart thing, since the whole purpose of this test is to see how close my prediction is to what we actually see. So take a freaking subtraction and subtract the things, right? Now, just to cut to the chase, do you remember when we did this with standard deviation, we subtracted the mean, the data point minus the mean? Didn't we have to square the damn thing? Remember that? Why did we have to square it? Because since some were negative and some positive, they would always add it to be 0, right? So we're going to do the same thing here. Let me see if you guys can handle this. So I'm going to do observed minus expected squared. So 21 minus 20 is 1, squared is 1. 36 minus 40 is negative 4, squared is... Square negative 4, you get 4 times 4. 16. Sorry. 69 minus 70 is negative 1 squared is 5. 5 squared is 25. 19 minus 20 is negative 1 squared is 1. Okay, hang tight. That is me capturing how far off my expectation was from what we actually observed. Now, now listen, if, let me see how I can say this. Yeah, here we go. If the prediction I made for something was like, I thought it was going to be 83 cents, and it turned out to be $1.20, isn't that relatively far off? You with me? Whereas if my prediction was $83 billion and it actually was $120 billion, relatively that's not as far off. I don't know if you guys are with me or not. Actually, I want to do this way. Let me do this way. Sorry. So this was what? This was 7, you could do it, Jeff, 37 cents off, right? So what if I had that exact same, this is better, Jeff, that exact same difference. So 83 billion was my prediction, and it turned out to be $83 billion and 37 cents. There we go, that's better. Is that 37 cents mean as much now? That's basically like, I got it right, period. Shit, I'm off by 37 cents when it was 83 billion. Are you kind of with me? Here, if I'm off by 37 cents, isn't that relatively huge? Okay. How do I capture that idea here? I'm going to take this divided by what we expect. That would give me a measure of the relative amount that I'm off by. If you understood my example that I eventually got right, about the 83 cents versus $1.10, blah, 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 is exactly the same idea. I want to capture the relative amount that I'm off by. So if I take, so this column is going to be observed minus expected squared divided by expected. So I might need some a little bit of calculator at some point here. 1 divided by 20, that's not that bad. That'll be 0.05. 16 divided by 40, that's pretty good. That's going to be 0.4, I believe. You guys can double check. 1 divided by 70, I don't know what the shit that is. It's 14.14 something, 57. I don't know. What is 1 divided by 7? D. Help me out. 0.014. Damn it. I was off by 1 decimal. 0.143?
Yeah.
Okay. Uh-oh. 25 divided by 50. Oh, shit. And then 1 divided by 20 again. Okay. Now, let me ask you this. If my prediction had been exactly the same as what we saw, what would I be getting everywhere? If my predictions were exactly the same as what we saw, everything would be 0. Yes, right? Everything would have been 0 if my predictions would have been exactly the same as what we actually saw. Is everybody with me? This captures how far off. Why does it not matter if it's how far above or below? Because we squared this shit, right? So it's just purely how far off were you? If I add this shit up, it gives me a general overall sense of how far the entire expectation was from all of the observations. So what do you guys get? Help me out. What do you get when you add all this stuff up? 1.0143? Maybe? I think that's what it is. I like how some of you are just staring at me. Like, I'm not going to help you. 1.0143?
Yeah.
Yes? Okay. Do the steps we've taken up here make at least a little bit of sense as to why somebody would go this path? Okay. Now, so we got this number. We currently are like, okay, it's a number. Yay. What does it mean? It's sort of like if on the first day I would have told you, hey, Z is 2.9. What do you think about that? You wouldn't like, Z is 2.9, I don't know. Now if I say Z is 2.9, what's your reaction? If I say I have a Z score of 2.9, anybody have any kind of reaction to that? Z score of 2.9. What can you tell me? Is that data point close to the mean? No, it's pretty damn, it's almost 3 steps away, right? So your immediate reaction to that should be, well, that's kind of relatively far above the average, right? This we don't have a feel for, of course, because this chi-square shit is new to us. Okay. How many categories were there? 5. How big was our sample that we took? 200. When I do this kind of analysis, the degrees of freedom will not be 199. The degrees of freedom, and I love this. I can't remember the book does this, but very often you'll see this. Categories, of course, starts with the letter K. Everybody knows that. I am so joking. But the official formula for some reason is K minus 1. K is the number of categories, which I just think is funny. Right? We're like, of course math people can't spell. So I had how many categories? 5. So what's my degrees of freedom? Holy shit. Okay, now. Let me stop for a minute. And by the way, I do have, look at this handout. Oh, it's not my writing. Thank the gods. Okay. So just bear with me for a little bit. For me, this is relatively good, to be honest. Like, yeah, for you, Jeff, it's relatively good. Okay. I didn't say what alpha was. What do you think we have to assume it is? 0.05. I love it. Can you take a minute and figure out, tell me what the chi-square score is? Alpha is 0.05. Degrees of freedom is 4. Say again, sorry. Let's see. Let's look together. 0.05 degrees of freedom is 4. Yeah, 9.488. So let me see if I can really get you guys with me. Remind me, if my observations had exactly lined up with my expectation, what would this have added up to be? 0, right? This, by the way, is chi-square. One formula for chi-square is this. How many formulas have we had for z-scores? We had like x minus mean over sigma, right? Then we had x bar minus mean divided by sigma x bar. Don't we have p minus p hat, or p hat minus p divided by square root of pq? Or, don't we have multiple frickin' z-score formulas that all relate to the same damn distribution? Yes? Yes? So we have this formula, and now we have this formula. Damn it, make a big ass E. There it is. The sum of the observed minus expected squared divided by the expected. The relative squared difference. Right? This is trying to be a summation symbol. Poor little guy. So this is exactly like the multiple z-score formulas we've seen. They all relate to the same picture. These two relate to this picture. Right? I should have made it more skewed, but too bad for me. If there would have been no difference, the chi-square we calculate would have been 0, correct? That would have been here. That would have been right there. If I take a sample, even if the reality is it does follow this, what if the reality is the population does follow this? If I take a sample, will the sample necessarily follow this? Let's say the actual average age of Grossmont students is 27. If I take a sample of students, does that mean their average age must be 27? If the actual average age of Grossmont is 27, and I take a sample of students, does their average age have to be 27? Shit, no, right? Every sample's got the chance for variability. I could just happen to pick a lot of younger people, a lot of older people, whatever, right? So, if it was exactly 0, that would not be evidence that it doesn't follow this pattern. Not only does it have to be more than 0, it's got to be more than 0 enough. Does that sound familiar? Not only do I have to be far away, I've got to be far enough away. So the thing we just figured out, this is like our rejection region. Did we make it far enough away? We got 1.0143, right? We're down here. Did we make it far enough away? No. Yeah, we didn't make it over here, did we? So again, let me say this again. Is everybody cool with the fact that if the actual population, if my sample exactly matched my expectation, chi-square would have been 0. So if chi-squared is not 0, that's an indication that the sample was different. What shows enough evidence that the whole population is different, since it's just a poor little sample, is not only does it have to be not 0, it's got to be really far away from 0 to account for the possible variation. So any sample that shows up in here is not good enough evidence that it's the same, that it follows this pattern. If I get so far away, then it's like, holy shit, it's more probable that it actually doesn't follow this. So can we say that it doesn't follow this? No, we didn't make it far enough away. So we did not find evidence that it does not follow this. So if this is what I think it was supposed to follow, I feel pretty good. I'm like, all right, I didn't disprove myself. Go me, right? Okay, maybe. I know this is some weird shit, so let me give you this. Instead of having to stare at my beautiful writing. We got a computer-generated graph. Holy shit. So take a minute, read through. Number one is an example I did for you. It's different from what we just did. Can anyone identify the fundamental difference between this one and the one we just did? By the way, I want to point out the name of this test is goodness of fit. I know some of you guys think that I made that up. That is the technical name for this test, the goodness of fit test. I always think about somebody with a little square hole and they're trying to put the round peg in. Come on. So how well does our observations fit what we expected? So that's where the goodness of fit comes from. So my first example is a bunch of M&Ms. What is it? So over here, the one we just did, the claim was it would follow this distribution, right? That was the claim. And that's how I figured out my expected. What is the claim here?
That they would be evenly distributed over like
Beautiful.
quarters.
Uniformly distributed, right? What would that mean? If they're uniformly distributed, every category should have the same amount. So I've got how many categories? 6, and I got 42 M&Ms, right? I think. Where'd it go? Yeah, 42. If you add up all the observed, they got 42. So how did I get what I put down for expected? Yeah. If I have 42 total M&Ms, and I expect them to be uniformly distributed, I would just take 42 divided by 6. That would uniformly distribute all of them. If I graphed it, they would all be a height up to 7, correct? Uniform. So either your problem could say, we expect them to be uniformly distributed, or your problem could look like what we did, or this next problem, where the expectation is given as percentages, right? So here, I wrote down what I observed. I wrote down the expected, so I evenly distributed all the M&Ms. If I did this for real, I would probably have a diminishing sample as I did this. Then I did what we did earlier, right? Took the difference, squared it, blah, 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 blah. So that would be my, what I would have called Z star in a hypothesis test. But I don't want to call it chi-squared star because it's already got squared up there. It looks a little freaky. But it's basically the equivalent of Z star. It's what I calculate for my sample. And then, can you guys verify this number? You never know. Past Jeff could have went insane. Where the shit did I get that number from? How did I get that? How did I get it? How many categories are there? 6. So what's the degrees of freedom? 5. Good old K for categories. And the 0.05 level of significance, I told you up here. So then you can just look it up. Make sure do you guys see 11.071 in the chart? You never know. Past Jeff, he does shit wrong a lot, that guy. Looks like he got this one right. Okay. So again, this example, did we find enough evidence? The beautiful thing about this problem is the rejection region will always mean, if you get in there, it will always mean you found evidence that it does not follow what we thought it would. If you don't get in there, we did not find evidence that it does not follow what we thought it would. That's beautiful. It's the only two things. So I'm not going to turn this, I could make this a complete hypothesis test. But no, I don't want to do that shit. I just get to the point, right? You guys have gone through it already. So can you please do number 2? It's just like the one we did a minute ago with the grades. Oh, as you do that, I'm going to give you the practice final exam. I thought I'd just give it to you early. Why not? So yes, we have a practice final exam. I'll have an answer key, all that kind of business. It's crazy. Well, that's weird. Why did I do that? So real quick, this should be 130. I don't know when that changed. Just in case you're curious, that should be 130. Okay, it makes me a little concerned. So what's that? 30. So that would leave 70, I think. No, wait. $390, 20, 432. So that would be 68, I think. Is that right? Oh. Some of you guys might realize that if you wanted to, you could actually do the work in the lists. Sweet. So let's see. You could do it, Jeff. Shit. What's that going to be? 25, 175? Why are you doing this in your head, Jeff? I think that's 75. That looks about right. Yay! Okay. Now, by the way, don't get too used to this. I'm being very nice. If I give you a problem like this, you're going to have to know to do this. Okay. Oh, that's right. I think. All right, keep going. Yeah, okay. So this is not a very large set of data, but if you wanted to, this one would be L1 minus L2 squared, right? If you wanted to. So you go to L3, parenthesis L1 minus L2 squared. You definitely don't have to do that. It's just, it's there if you want to. So then I can just copy that shit down. Is that matching up with what you guys got? Okay, I got one thumbs up. Okay. And then this one was going to be L3 divided by L2. So go up to L4. I can make the L3 divided by L2. And again, you don't have to do any of this shit if you don't want to. You just do each row. Doesn't really save you a ton of time to do this. The nice thing about doing it this way is I could do that little thing we did earlier semester. I could just say, all right, calculator, quit. I could say list math, sum, L4, shabam. Okay. Is that all right? What's up? I don't know. Oh, sorry. This here? Yeah. Remember doing that? And it doesn't matter. It doesn't really save you that much time. I'm not going to give you a list of 80 freaking categories. See who goes insane first. No. What is this, by the way? What did we just calculate? Chi squared. Never square root that poor dude. That square is a part of its name. Okay. Now, how do I check to see... This is a little backwards, but this kind of makes sense. We just go right to the actual data. What else do I need to set up? Bless you. Need to draw my little skewed right dude. What's alpha? 0.01. I love it. So alpha's 0.01. What's the degrees of freedom? 3. So take a minute, look that up. What's the critical, what's the rejection region chi score? Chi squared. Anybody? So 0.01, 3, yeah, 11.345. So where did we get? We got 17. Chow. Did we find evidence of something? What did we find evidence of exactly? The people in this secluded area, their cholesterol levels do what? I love you guys. So we had an expected way that they would fall. Did they fall the way that we expected them to? No. Good. That's the whole point. Zero would mean they completely lined up with what we expected. So if I get past this, they did not line up with what we expected. So the people in this secluded area, we have found statistical evidence that they do not have the same cholesterol levels as the general population. In fact, more precisely, can anyone tell if they have better or worse? Is it better to have low cholesterol? By the way, this is I don't know if you guys know about HDL versus LDL. This is LDL is bad, right? Let me show off my amazing knowledge. I don't know. LDL is bad. So let's say this is the bad stuff. Are they generally better or worse? How do you tell? Did more of them have lower than expected? 111 had lower than 130. We expected 100, correct? 184 had between 130 and 200, which is still good. We expected 150. And then less had higher amounts of cholesterol, correct? Do you guys are too young for this, maybe in your history class. Back in like the 80s or whatever, a lot of weird shit happened in the 80s. I don't know. I lived through it. It was neat. We noticed, I can't remember right. I might have told you about it. People in the Mediterranean, have I talked about them yet? Yes. Okay, that whole thing. This is basically what they saw. But what they didn't do, this is very surface level shit. All we know is that there is evidence that people in the secluded area have lower cholesterol. And of course, what did we do? Being Americans, we said, what's the easiest thing? Oh, olive oil. They all do the olive oil. Shove that shit on everything. Right, because it's easy. We can buy it. We can get it. It can't be the fact that they walk everywhere. No. It can't be the fact that they eat more fish and, lighter stuff. No, that's weird. Just pour some olive oil on that freaking Big Mac. No, thankfully, I don't know if that happened. That's a little extreme, but are you guys at all with me? I mean, this is something that happened, right? And it still happens. I mean, we still get that kind of shit happening. So what would I write here as a conclusion. Does anyone have a guess as to what I could write here? I basically said it a minute ago, but did we find evidence of something? Yeah, we have found evidence that what? These people have, well, we can just say this right now, different cholesterol levels than the general population. I went a little further. Those are words, by the way. I went a little further and said, oh, we can actually tell that it's better. So this says, we have found evidence that these people have different cholesterol levels than real published. So just to remind you, if I get into the rejection region, that is evidence that it's different from what was expected. If I don't get in the rejection region, that's not evidence that is different from what was expected. Now again, I saw the looks in your faces when I said I had another chart. You looked very excited. This chart, not that terrible. We've already been through a couple, so it's not terrible. This problem, I didn't make it a full-blown hypothesis test, right? We do the most important parts. What's the most important part of any hypothesis test is step 3 and step 4. Where's evidence start? Did we find enough evidence? So we just jump straight to that, right? So I'm hoping this won't be too evil. I've left some things for you to read when you do your homework, just to make that clear, right? Me plus book equals class, yes? So this book does some things well, so you read that section. Other than that, I'm done. That's all I have for today. So, so I'm sorry if you wanted more class. We are done for today. Let me know if you have any questions or anything. Otherwise, I will see you next week. Oh, quiz Monday. Correlation. I'll have one correlation problem. You'll need to put it in the calculator, line of best fit, come up and show it to me, just like I said. It's like Columbo. Oh, one more thing. Sure. Quiz for the people at home.